In the late 19th century, physicists testing the boundaries of electromagnetic theory hit a glaring contradiction. It appeared right here, for instance, in the simple interaction between a moving magnet and a conductive copper coil. According to the prevailing science of the day, Maxwell's equations, this single interaction was explained using two completely different sets of rules, depending entirely on which object was assumed to be standing perfectly still. If the coil rests and the magnet moves, an electric field forms around the magnet, pushing current through the wire. But if the magnet rests and the coil moves, no electric field appears. Instead, an electromotive force arises within the conductor itself. The paradox lies in the physical measurement. Even though the theoretical causes are entirely different, the measurable result, the electrical current flowing through the wire, is exactly the same in both magnitude and path. The coil and the magnet do not know who is moving and who is stationary. Nature only cares about the relative motion between the two objects. This singular observation proved that the classical assumption of an absolute stationary background is physically meaningless. In 1905, Albert Einstein published a paper addressing this exact problem. Looking at this text, he begins by noting that Maxwell's electrodynamics leads to asymmetries which do not appear to be inherent in the phenomena. He proposed elevating this suspicion into a formal postulate. He called it the principle of relativity, the premise that the laws of physics apply equally in all coordinate systems moving at a constant speed relative to one another. Then he introduced a second postulate, one that immediately seemed to contradict the first. He stated that light in empty space always propagates with a definite velocity, v, entirely independent of the state of motion of the emitting body. Reconciling these two axioms, that physics is relative, but the speed of light is absolute, creates an immediate logical crisis. To solve it, we have to discard our physical intuition and rebuild the definitions of space and time from scratch. Classical mechanics assumes time is a universal, invisible ticking clock shared by everyone. But to measure anything physically, we first have to rigorously define what simultaneous actually means. Einstein devised a strict physical protocol for establishing time within a stationary coordinate system, which we'll call System K. We place an observer with a clock at point A and another observer with an identical clock at point B. The observer at A sends a brief flash of light toward B. The exact moment it arrives, B reflects that light signal directly back to A. We record three specific variables: the departure time from A, the arrival and reflection time at B, and the final return time back at A. Looking at his derivation, Einstein sets a firm mathematical rule. These two clocks are only synchronous if the time required for light to travel from A to B is exactly equal to the time it takes to travel back from B to A. This protocol uses the constant speed of light, v, as the ultimate unvarying measuring stick to establish a shared sequence of events across different physical locations within System K. Measured time is no longer an abstract philosophy. It is now a rigidly defined physical property, inextricably bound to the finite speed of light. Now we test this definition on a moving object. We take a rigid rod of length L, place it inside our resting system K, and give it a uniform parallel velocity, lowercase v, along the x-axis. To understand how motion affects space, we measure this moving rod using two completely different operations. In operation A, an observer moves alongside the rod at the exact same velocity, measuring it by laying a physical ruler directly against it. Because of the principle of relativity, the co-moving observer experiences the rod as being perfectly at rest. They find that it still measures exactly length L. But in operation B, stationary observers in the resting system K measure that same moving rod, relying on the synchronized clocks. They must note the exact coordinate positions of the rod's front and back ends at a specific simultaneous time, t. But here is the critical flaw. Because the rod is moving forward, a light signal sent from the back of the rod to the front has to chase the rod's motion. It will mathematically take longer to reach the front than a signal sent from the front to the back. Consequently, the observers moving with the rod will disagree with the stationary observers. Their timeframes are out of sync, meaning they will disagree entirely on whether the endpoint measurements happened at the same time. This forces Einstein's primary conclusion. We can no longer attach any absolute meaning to the concept of simultaneity across different frames of reference. Two events that are perfectly simultaneous when observed from one coordinate system are demonstrably non-simultaneous when viewed from a system in relative motion. This creates a direct mathematical challenge. How do we translate coordinate measurements between the resting system k and the moving system k while ensuring the speed of light remains constant for both? The classical Galilean transformation equations fail because they assume time is an independent, universal variable. To solve this, the coordinates of space and time must physically intermix. Einstein derived a new set of transformation equations. Looking at this block, you can see how both the spatial position and the time in the moving system are now intrinsically dependent on the velocity, v. Notice the scaling factor, beta. This term acts as a mathematical governor, strictly enforcing the speed of light limit across all spatial calculations. To see the physical reality of these equations, Einstein asks us to imagine a perfect rigid sphere. We place it inside the moving system and view it from the perspective of the resting system. The math dictates the y and z dimensions remain unchanged, but the x dimension does not. As measured from the resting system, the sphere physically compresses along its axis of motion, morphing into a flattened ellipsoid governed by the velocity ratio. This is not an optical illusion. Length contraction is the objective, physical geometry of a moving universe when measured from a resting perspective. Let's apply this twisted geometry to one final paradox: how speeds combine. Imagine a fast-moving object firing a secondary projectile straight forward. Classical mechanics dictates a simple addition. If a system moves at a velocity of v and a point inside it moves forward at a velocity of w, the total speed should simply be v plus w. But what if the system is moving at 80% the speed of light, and it fires a projectile at 50% the speed of light? Classical addition gives you 130% the speed of light, openly violating our strict upper limit. Einstein solves this with his new formula for the addition of velocities, which fully incorporates the spatial contraction and time dilation we just proved. Look at the denominator. That bottom term acts as an absolute mathematical dampener, adjusting the output to ensure that no combination of speeds will ever exceed the constant v. Classical addition fails at high speeds because the physical ruler measuring the space has shrunk, and the clock measuring the time is ticking slower. Now push this formula to its absolute extreme. What happens if that secondary projectile isn't a physical object, but a beam of light moving at exactly velocity v? When composing any arbitrary velocity with the speed of light, the math requires that the output can never exceed the speed of light itself. If you plug v into the equation, the algebraic reduction is perfect. It entirely absorbs the system's velocity, collapsing down to return exactly v. This algebraic result exposes the rigid geometry of the universe. The speed of light cannot be altered by compounding it with any other velocity. Space and time are not a static stage where physics happens. They are dynamic, flexible variables that will physically contort themselves to enforce a single cosmic absolute, the constant speed of light.